Okay, I guess Davis, can you hear me? Say online.
Yeah.
I hope you can. Right. Okay. Good. So last time we started talking about random matrices, and the result that we want to show now is this bound on the operator norm of sub-Gaussian matrices. So if you have a sub-Gaussian matrix, by which we mean a matrix whose entries are independent, zero mean, and sub-Gaussian, the sub-Gaussian norm is bounded by k. Then with probability 1 minus e to the negative t squared, the operator norm is going to be controlled by this quantity. And we talked a little bit about why this is a good bound. If you just look at a deterministic matrix where every entry is k, it's not hard to compute the operator norm. Perhaps the easiest way is to compute the Frobenius norm, which is the same as the operator norm. And it turns out that this is k root mn, which is much bigger than root m plus root n. So the idea of the proof of this, at least the proof that we're gonna work through, is to use the discretization argument, the metric entropy ideas. Okay, so suppose let's start with this. So recall that the operator norm of the matrix A is defined as this quantity. Okay, so maximum over the unit ball in Rn of Ax, L2 norm of Ax. And another way of writing this is to maximize over the unit sphere. If you recall, Sn minus 1 is the set of all x such that norm x is equal to 1. Okay, so this is that. The ball is the set of all x such that norm x is less than or equal to 1. Anyone remembers why this was the case? Why can we like pass through this? Yeah. Yeah, great. Yeah, so this is like a convex set. It's a convex function. Maximizing over it is equivalent to maximizing over the extreme points, and the extreme points are this sphere, like the union is the sphere. And then we have also this characterization, which sometimes is useful. So why is that one useful? Or like not useful? Why is that true? So I can like do ax, y, inner product x and y in on the sphere. So if you recall, we did something like that, and we tried to prove that technical result about like generalization of the restricted eigenvalue condition. We use this sort of idea to. It was like a Gaussian process here, and then we like compared it with a simpler Gaussian process. So why that statement is true? All right. Okay. Yes, that's right. Another way of saying it is that I can write for any vector, I can write the L2 norm as, let's say, y in Sn minus 1 uy. So this is a representation of the L2 norm. And so if I replace this L2 norm with this representation, I get this. Okay, so that's the dual representation, and the L2 ball is self-dual. Okay, so the point now is what I can do is that I can use, so the supremum here is over an uncountable set. Either one of these is uncountable. And then we can use the epsilon net ideas, or basically discretization ideas, to reduce this to a supremum over a finite set. So if I take this, so suppose I have a net, epsilon net, if you recall, like this script, and if we call it, let's say I have an epsilon net, which we call script and of either the ball or the sphere, then the operator norm is lower bounded by the supremum of this L2 norm of AX over the net. Right, this one is easy. Why is this the case? Right, yes, so N is inside, by our definition, epsilon nets are inside the set, so the supremum over a smaller subset is less than the supremum over the bigger set. And this is the more critical part. And it shows that, so if I take, for example, epsilon to be 1/2, right, this would give me 1 over 1/2, which is 2. So this tells me that the operator norm is within a factor of 2 of the supremum over a 1/2 net. Okay. And so I'm going to lose just a factor of 2 when I pass to a net with epsilon equal 1/2. And then a similar result is true if you try to do it here. You would get, we'll go through the proof of this, and then you can just, as an exercise, try to show that if I replace the x and y by respective nets, so x and y have different dimensions, right? So I forgot how yeah, so it's m by n. So x is in Rn, and then y in our case is in Rm. Yeah. This one? I'm going to show that. Yeah. I just realized that this is not correct. So this has to be, sorry. X is in there and y in Sm minus 1. Because this is m by n. And so, yeah, so once you show that, you can show this, there's like a factor of 2 here. So let's try to show now this inequality, right? So how do we show this? Any idea how to show it? You can rearrange and say 1 minus epsilon. Operator norm is less than or equal to sup. X is n, n. And then, like, if I rearrange further, this is operator norm less than or equal to sup. X is in n plus epsilon. So you want to show this. Yeah. Okay, great. So let's try that. So I'm going to define this projection, which we probably haven't choose here. I'm going to project from, let's say, Sn minus 1 to the net. So pi of x is the closest point in n to x. So by definition, pi of x minus x, the norm, would be bounded by epsilon. Okay, this is the definition of an epsilon net. Okay, then what should we do? You can write a triangle inequality, right? So I try to write this as a, let's call this pi x. Let's do it like this: ax minus a pi x plus a pi x. Do the triangle inequality ax minus pi x plus a pi x. So next, what should we do? Left one, this one? Less than operator norm of a times which is less than or equal to epsilon a. Right, this is by the definition of the operator norm, if you recall. This is one of the main properties of the operator norm. So, and that's by definition of the epsilon net. So okay, so what I would get here is epsilon a plus a pi x. So now what should we do? So take supremum. Okay. And then I get epsilon a plus sup over x in Sn minus 1. So what should we do next? Yeah, so that's the case. So this is like sup over, as x varies in Sn minus 1, this pi x is just going to vary in n. So you get these different, it's equivalent, or I think that's less than, yes. Going to be precise, it's less. Let's say call this z in n a z. Okay, and that's the result I wanted to prove, which is this guy basically. Okay, so this is an operator norm. So you're saying it's like you pay a price. These are all operator norms, by the way. This is op. So the price that you pay by doing the discretization is epsilon times the operator norm, and then plus this quantity. So you move things around, you get 1 minus epsilon. A operator norm is bounded by sup az, and then divide. Makes sense? So the interesting thing is like this property of the operator norm that allows you to sort of say that if I apply to this deviation, basically, I'm going to pay the price, which is operator norm times the difference, which is of like a smaller version of itself. So you just, this argument need not always work, but the discretization argument is like this. So you just compare your function over the entire set to the function over the net. If you can control the deviations. So there are two steps. One, the deviation of the function to the value that's closest in the net. And then there is a part which is usually by triangle inequality or some other inequality. It's just a function over the net, the worst case. This one, if you can control, which in this case nicely, yeah. Yeah, that's basically. So in the notation that I'm using, the operator norm is just the L2 norm, like the 2 norm. But you can imagine this argument goes through. Let's say if there are different operator norms, right? So you could put different norms here and here. You get like a PQ operator norm. This argument sort of goes through, right? At least let's say if I have a Pete operator norm. If I'm not wrong, if you, so the epsilon net here has to be like an epsilon net of the P ball in the P norm which we have seen has the same sort of cardinality. So if you like cover a ball in itself, like the norm of itself, it doesn't matter. So if you go through this argument, if I'm not wrong, as an exercise, go through it, it works for any like Pth operator norm just fine. If you do PQ, yeah, I'll encourage you to go through and see what needs to change. But the only thing that we have used here is this property of operator norm, and you can see if it's like PQ, then I have to control the qth norm of this. So I need a net, the qth net, and then Q, I think, I think it measures well. But the thing is that this net is going to be, for example, an LQ cover of the LP ball, but the rest should go through. Yeah, to simplify, we just work with the peak norm. Okay, but it's a good point. Okay, so we prove this. Questions? So what I'm going to do next is take the epsilon to be 1/2. So I'm going to pay a price of 2. So instead of bounding this, I'm going to bound the supremo over the net. And because we just absorb the constants into this, I'm just not going to worry about the 2 anymore. So how do we control something like this? What is the idea to bound this guy? So let me remind you that A is a matrix like this. Lipschitz functions, it works for Gaussian setting. So what is the general sort of like the first sort of step? Yeah. Usually you need a tail bound. So what do we need to control? How do you like bound the maxima or supremo of something? Like union bound. Okay, so we're going to use the union bound. So let's say well, actually I'm going to do it's easier to do this version. This one works as well, but I'm going to use this. Okay, so let's try to do this. Let me do this. So take epsilon to be 1/4, and M and N be like the nets of Sm-1 and Sn-1 from the result that we showed. The operator, sorry, the metric or covering number of this ball is bounded by 3 over epsilon to the d. If epsilon is less than or equal to 1. So if I take epsilon to be 1/4, this did not work really well. Why do we get 9 here instead of, so I plug in 1/4. Yeah, okay, so forget about it, just use the actual bound, okay? The 9 doesn't matter, 12 is as well, I mean, good enough. But if I put 1/4 here, I get 9 to the d. So the key is that the epsilon nets of like constant radius are exponential in dimension, okay? So I have this many points, and then I have the operator norm, which is, so if I take the 1/4 here, and take 1/4, this turns out to be 2, right? So I'm going to now restrict myself to this quantity. And what I'm going to do is now say the probability of, I want to control this, x in n, y in m, a x y bigger than or equal to t, let's say, by union bound. What can I write by union bound? How do you union bound usually? Yeah, this is the union of these events. X in n, y in m, a x y bigger than or equal to t. That's the event. So you get summation x in n, y in m, probability a x y bigger than or equal to t. And usually you bound this uniformly. The quantity usually doesn't depend on x and y. But let's see. So that's the first step. Now I have to control this for a fixed x and y. So I know fixed x and y. And I would like to have a bound for this. Okay, so let's move this up here. So now fix x and y. Drive a tail bound for ax y. So A has entries aij. There's zero mean, and sub-Gaussian norm is bounded by k. So how should we proceed here? Let me remind you what this looks like. This is summation I, summation j, aij, xi, xj. I from 1 to n, j from 1 to n. Sorry? Yj, right. So what can I say about what kind of random variable is this? Sorry? Sub-Gaussian. Why? Great, yeah. So sum of independent sub-Gaussian random variables. That was a result that we had, right? So the only thing that I have to worry about is how big, yeah, let's say psi 2 norm is, or sub-Gaussian standard. So what do we know about the sub-Gaussian standard of this? Like the sub-Gaussian norm behaves like the variance for independent. Exponent minus. This is similar to the sub-Gaussian parameter, sigma, right? So there's a property, if I sum a bunch of sub-Gaussian, independent sub-Gaussian random variables, something happens to the sub-Gaussian standard or the norm. Right? Remember the property. Sorry? Less than or equal to the sum, that's true. But this is not a good bound. So it's true because this is a norm. This works because it's a norm, but this is not a good bound. Let me remind you, like it's easiest to recall just what the definition was. So I have like x1 up to x, let's say n, they're sub-Gaussian with standard. Okay, I should say like max. Max is not the right thing either. There's a better thing. So Sorry, so let's recall what this is. So these are sub-Gaussian if something like this holds, right? For all lambda in R. Okay, and they're independent. So now I just have to compute the MGF of the sum, right? Which is the expectation. It's actually equal to expectation of the product e to the lambda xi. Right, you know what happens here, right? So you get product over I e to lambda xi less than lambda squared sigma I squared, which is equal to e to the lambda squared sigma I squared, right? So I can say the sub-Gaussian standard of the summation is like bounded by summation I from 1 to n of the sub-Gaussian standard of individual ones. Okay, it's like the variance. It's like a square. So and then the sub-Gaussian standard is up to constants the same as the norm. So this is just saying that psi2 norm squared is up to constants. Now this is like tilde here, I from 1 to n xi psi2 squared. Okay, instead of doing this, then it's a loose bound. You'll see why this is loose shortly. This is a much better bound. So what I get is that if I square this up to constant, this is bounded by the square of these. Okay. Now what we can do here, or what can we do here? Now let's use the property of the norm, right? Xi and Yj are constant, like they're not random. What can I do? Pull them out, I get xi squared, yj squared, and then aij psi2. Now I'm going to use the fact that the maximum of these is bounded by k, like all of them are bounded by k. So this is going to be bounded further by k. That's by assumption, I from 1 to n, j from 1 to m, xi squared, yj squared. So what is the next step? Right, so this factorizes basically. So summation over xi's, yj's. So this is saying k norm x2, 2 and norm y2, 2. So what are these norms? So they're in the sphere. So you're assuming that they're on the net. So x is on the net, which is a subset of the sphere in n-dimensional space. And then this is also on the sphere. By assumption, our nets are inside the set. So these are both 1. So the amazing thing is that the sub-Gaussian norm of this complicated sum, as long as the x and y are on the sphere, is no worse than the sub-Gaussian norm of the individual terms. So if you go through this argument, you'd get a very large. Just try it. So this symplectic effect doesn't happen. So you basically get the L1 norm of xi and yj, and the L1 norm. So you get the product of the L1 norms, and the L1 norm is like root n m. Like the L1 norm of x1 would be up to like root n times the L2 norm, and then so this would become really big. Like the bound that you get is really big. Sorry? I think so, yeah. So you could get a bound like k root mn, which is really bad because this is the scale that you expect the actual like the worst case to be, but we haven't even used the union bound yet, which adds to the complications. So this is not a much better bound. Okay. So now that I know that the psi2 norm is controlled, I can write a tail bound for this. Yeah.
This problem was the sub-Gaussian norm plus the equal k or was it square?
No, the sub-Gaussian norm. Oh, right. You're right. Thank you. There is a squared here. This is k squared. And k squared. Yeah, it should be k squared because we're looking at the square. So the psi2 norm is bounded by k. Thank you. Okay. Now how can I write a tail bound? So I want to say, so what is the mean of this, by the way? Sorry? This is zero mean, right? So it's a zero mean. It's a linear function of aij. So zero mean, sub-Gaussian random variable with the sub-Gaussian norm being k at most. So I can write a tail bound for this, right? So the probability that, so from the fact that axy psi2 is up to constant k and the expectation is 0, I get that I can write a two-sided tail bound, let's say, or actually can write a one-sided tail bound. Someone asked why you don't have a 2 here. And the reason is we can just do like a, it doesn't matter, but it's just enough to do one-sided. So this is basically the same as the probability of ax y minus the expectation. I'm doing an upper tail, right? So what can I say here? Yes, great. Exactly this. If I want to simplify, let's see what we have here. Yeah, I have like a negative t squared. What I can do is just, let's say, replace. So let's do u here. Right, like take u to be just k divided by root c t. Okay, to get I get the probability that ax y is bigger than or equal to like k divided by root c t is at most e to the negative t squared. Okay, I can just push the constants here, get a clean probability bound. Okay, and I'm just gonna call this 1 over root c. It's just another constant. So this is like, say, c1k t. Okay. Call this that. Now we go here, right? We had this. Take this, copy, and then we go down here. So I have this, right? Now my bound is, this is bounded by summation x in n, y in m. Sorry. So the probability that this is bounded by C1 KT, same goes here, bigger than C1 KT. This is bounded by e to the negative t squared, which is bounded like is equal to cardinality of this, cardinality of that, e to the negative t squared, right? The problem is that these are, so this is like 9 to the n, 9 to the m, you see the exponential nature. So these are exponential in dimensions, but they also have an exponential tail here. So now can we, what I want to show is something like this, recall. I want to show something like that. So how do we show something like this? So I want the probability of this x, y, x and m, n, y and m, a x, y, bigger than c1, k. It's actually like, I'm going to just absorb the constants. Just say something like that. K times root n plus root m plus, I'm going to say delta less than or equal to e to the negative delta squared over this. We already did union well, right? So I want to kill basically these two terms. Let's say I just can pick t appropriately to counteract these two. So if you look at this, this is just 9 to the n plus m, right? E to the negative t squared, which is, so put it out there, which is equal to e to the log, sorry, n plus m log 9, right, minus t squared. Okay, so now if I take t squared, let's say t is root n plus root m plus delta, let's say. And I want, let's say, 2 log 9. Right? If I do this, what I get is that t squared is, okay, let's do, 2 is good, but root 2 also does. So root 2 is squared, you get 2, root 2 log 9. So I get 2 log 9. And then the square of this is going to be bounded by n plus m plus delta squared times 3. Oh, sorry. I want a lower bound. So this is going to be bounded by this. Because the things are negative here. A lower bound would be just this squared, this squared, this squared, when the cross terms are all not negative. So I drop them, I get that. So you can see this is going to be upper bounded by e to the n m, like log 9 minus log 9 minus 2 log 9 n plus m minus 2 log 9 delta squared. Right, so this part is just negative. Right, it's like the same thing, but twice with negative sign. So this thing is going to be bounded by 1. So I get this bounded by e to the negative 2 log 9 delta squared. And this is the bound that I want. So this is like, you can see t is like c1 root 2 log 9 and then there's a k, and then there's root n plus root m plus delta. And then you can also just adjust this, just get rid of this, put it here, call the whole thing the constant c, and then you're done. Okay. So the main step is just to kill these two. I just need at least root n plus root m, and I also like to put something here for later use, because later on I can just adjust this and then control the probability. Okay, that proves the result. So you can see the reason why these appear here is, roughly speaking, the fact that these are exponential in n and m, and then you have t squared here. Okay, the root n squared would like kill this, root m squared kills this, and then the rest follows. Okay, sounds good. Okay, this is a nice example. So the ideas are simple, sort of, but the result is non-trivial. For a Gaussian case, like if you have like independent zero mean Gaussian, and the variances of the entries are 1, you can show a much sharper result. So you can show that the operator norm is basically root m plus root n plus t with probability this much. And the idea is basically using the concentration of Lipschitz functions for Gaussian vectors. So the way that you do it is, if you recall, operator norm is a Lipschitz function of the entries. Remember this, because we want to basically say that Lipschitz has to be with respect to the Frobenius norm. So operator norm. So if I define f of x to the operator norm of x, then f of x minus f of y is bounded by x minus y. This is the triangle inequality for the operator norm, and this is bounded by the Frobenius norm. And so Frobenius norm for the matrices is just the vector L2 norm. So this is saying that this function is a Lipschitz function of x as a vector. And if x is now Gaussian, a Gaussian matrix, which is a giant Gaussian vector, standard, then you get this concentration, right? Operator norm minus this expectation bigger than t. It's 1 Lipschitz, so you get e to the negative t squared over 2. This is just immediate from that concentration of Gaussian measure. The only thing that you now have to control is the expectation of the operator norm. This is very similar to the argument that we did for that restricted eigenvalue condition, but we're doing like the lower bound, like the minimum eigenvalue here is like the maximum singular value. And using the Gaussian comparison inequality, it's like a simpler version. The Slepian one you can actually show. Remember, this is like, this is basically expectation supremum over x in Sn minus 1, y in Sm minus 1, axy. And if you go through the argument that we did there, so you can compare it with some simpler process, like expectation over, actually we didn't do Slepian, but Slepian is simpler. You can compare it with the process that has like gx plus hy, with g and h appropriate Gaussian vectors. You can show that this is like that, so using the Slepian lemma. Just check out the Gaussian comparison inequalities in the book. The conditions are satisfied. So this is, sorry, the supremum here. Soup over these of this process. And then this breaks into two pieces. So break into two pieces, basically, it just would be expectation of the norm of G2 plus the expectation of the norm H, and the norm, so G and H, so G is normal mean 0, h normal means 0, and this. And this you can show is easy to show that this is bounded by root m, root n. This is bounded by root m. So the only tricky part is just figuring this out. But if you go back as an exercise, try to figure this out yourself, then this simplifies and this gets you that. This is just Jensen's inequality. So root expectation the square of this, which is n. So this gives you a very sharp bound. We can say if you're interested, go through this argument for yourself. And it can't get much better than this. So it's like there should be a lower bound, like 1 minus O of 1 root m plus root n for the Gaussian case. We are not doing the lower bounds, but the order is right. And the constants are quite tight here. Okay, for the Gaussian case. Just good to remember that if you have a standard Gaussian random matrix, the expected operator norm is bounded by this. And then you also have this concentration. So you get this very nice little result there. Okay. Okay. Yeah, so you get a better constant basically here. So you can get a, sorry? The rate is the same, yeah. So the nice thing about this result is that you get the right rate. The constants we didn't care much about. So up to, and usually this is, for the Gaussian case, this is just another constant, right? So you get the different constant here. With this result, you can get it. And then this is sort of elementary. This argument that I did basically relies on two very sophisticated results. One is this fairly sophisticated, it's not that sophisticated, but this is, this we haven't proven or haven't talked about actually. It's in comparison inequalities. We compare the supremum of one Gaussian process to another Gaussian process. Their deviations have to satisfy certain conditions. Basically, a Gaussian process has a metric, and the metric for this has to be bounded by the metric for this. And then there's this very high-powered tool, which is concentration of the Lipschitz functions of the Gaussian vectors, which we haven't proven. The argument is very short, but it uses very powerful tools. And the above argument, this argument is more general, so you can adapt it to your setting. You can prove more. You will see we'll use this similar technique to do covariance matrices, so concentration of more fancy stuff. Okay, sounds good. Questions, comments? Okay, let's move on then. I want to take a detour, introduce this idea of a sub-Gaussian vector, which is from the high-dimensional probability book, this section 3.4. So if you have a random vector, so if you recall what a Gaussian distribution is, right? So how do you define actually a multivariate Gaussian, if you recall? We know how to, yeah.
So every subset.
That's great, but that's not enough. Yeah. So every subset. So if I want to define the Gaussianity of a, sorry, let me try to open. Let's do it here. So if I have a vector x1 up to xn, I want to define, let's say, the multivariate Gaussian. So one property is that every subset of coordinates has to be multivariate Gaussian. It might actually be enough, but then you have to define what you mean, right? It's like you reduce the problem to, yeah. Yes, that's the way to do it. So you want to reduce it to the one-dimensional case. So if you have, so you can say this is this if and only if like ux, this is x, is Gaussian for any vector u. Basically, you would say summation ui xi for any linear combination is Gaussian. And then I can actually compute the MGF, and then you can actually invert, or the characteristic function inverted, you can actually get the PDF. That's one way to get the PDF of the multivariate normal. So the same idea, say this is Gaussian with, this is enough to say just it's Gaussian, then we can sort of figure out the rest. The same idea applies to, but at least this definition tries to mimic the way we define multivariate Gaussian to define a multivariate sub-Gaussian distribution, say that X has multivariate like sub-Gaussian distribution as a vector. If U inner product with X is sub-Gaussian for every U now in S d minus 1. So if it's true, then it's true for every U because I can multiply by any constant, it's still sub-Gaussian. The reason why it's restricted to this sphere is that because we want to define the norm as well. So we define the sub-Gaussian norm of X to be the supremum of the sub-Gaussian norm of these, let's say, one-dimensional projections as U varies in this sphere. Okay. Why this is useful, you'll see. So the first thing, for example, to note is that if I have independent sub-Gaussian coordinates, so if X has independent sub-Gaussian coordinates, by the property that we just used, U X will have psi2 norm bounded up to constants by summation ui squared, psi2 norm of this, and this is, let's say, all of them are bounded by k squared, so this is going to be bounded by k squared, norm u squared, which is 1, so this is k squared. So this is saying that this is going to be a sub-Gaussian vector with sub-Gaussian norm, which is bounded by k, the maximum, up to a constant. Okay, so sub-Gaussian vectors with infinite sub-Gaussian coordinates are sub-Gaussian with this norm. The other cases where things are not independent, this is the case where you have uniform distribution over the sphere of radius d, root d in R d. Then it's a sub-Gaussian vector with constant sub-Gaussian norm. The canonical Gaussian is the same. Like this follows easily from this. The more interesting is like a multivariate Gaussian with zero mean. This has this is a sub-Gaussian vector with sub-Gaussian norm bounded by the square root of the operator norm of either this or this is equal to square root of the operator norm of this. So this one is close to this because this uniform distribution is very similar to the Gaussian. So if you have a Gaussian, say in RD, you know that the L2 norm is very close to root D. And so X over, basically X over, if you have a Gaussian like this, X over X is unit norm, and by spherical symmetry, this is, maybe do it here. If X is normal, means 0. So X over this is going to be like uniform on this sphere d minus 1. This is exact, okay? You can imagine this has unit norm, and the distribution has to be like uniform in every direction because the Gaussian is symmetric. So if I multiply it by root n, by root basically D, I get x divided by norm x. This is going to be in uniform root D SD minus 1. So this vector is going to have the same distribution as this. And with high probability, this norm is very close to root D. So sort of you can imagine there's like some hand-wavy argument that I can cancel these, and then x has to be behaving similarly. So uniform on the sphere of root D is very similar to a normalized, basically Gaussian. And so they go hand in hand. So if you have a result for this case, usually you can transfer it to this and vice versa. This case follows from this using this next lemma. I can write x as root sigma times z, and then z is normal mean 0 and identity covariance. Then I'm going to apply lemma 1. What is lemma 1 here? I'll leave it to you to prove that if I have a sub-Gaussian vector and A is a deterministic matrix, then AX is a sub-Gaussian vector. And the sub-Gaussian norm of AX is bounded by the operator norm of A times the sub-Gaussian norm of X. This follows from similar properties for Gaussians. But try to prove this, or I should assign probably as a homework problem. It's like exercise. Proof left as an exercise. Okay, sounds good. So now we're ready to state and hopefully prove this result about concentration of sample covariance matrices. So suppose I have a design matrix. This is the classical situation in statistics where we have observations, right? And then I have D here. Usually, I mean, maybe high dimensional, maybe not. At this point, we don't care. D, and then the ith row basically is one observation. So this is, I'm going to call this, you can call it x1t. So xi is like a column vector, xit is a row vector. That's the ith row. And so the rows are independent, but they have correlation across columns. So xi, you're assuming to have covariance. So am I assuming? I'm not assuming actually. Yeah, the thing is, this is not necessarily covariance, but let's say if xi's were zero mean, then I'm going to assume the covariance to be sigma. What this result is showing is actually, we just assume that the second moment matrix, this is the second moment matrix is sigma. If things are zero mean, this is just the same as the covariance. If not, the result that we're going to prove something about estimating the second moment matrix. Okay, there's a difference with the covariance matrix. So covariance of xi is the second moment matrix minus there's a first order term like the mean, right? Mu transpose where mu is the expectation. This one you can separately control. This is the key part. So the result doesn't require zero mean assumption, but then sigma would be the second moment matrix, or assume the zero mean assumption, and sigma would be just a covariance matrix. So I want to estimate either this or the special case, the covariance matrix. So what is a good estimator here? How do you estimate? Average, yeah. So you just replace this with the empirical average. So I get 1 over n summation I from 1 to n, xi transpose. This is sigma hat n. So that's a very good estimator. Sort of, not the very good, but the most natural estimator. This is unbiased. Right? So if you take the expectation of both sides, the expectation of sigma hat n is equal to sigma. So it's an unbiased estimator. And we want to show that sort of it's consistent, or how close it is to sigma. So we want to basically control sigma hat n minus sigma. And you're going to do it in operator norm, which is really nice because if I have control in the operator norm, then if you recall, there's this Thales theorem that we saw towards the end of the concentration slides that allows you to control the deviations of all the eigenvalues. And you can also control the deviations of the eigenvectors using things like Davis-Cohen theorem. So operator norm is very nice for controlling the spectral properties. So we're going to prove this in operator norm, and the result is something like this. Okay, so I can also write sigma hat as 1 over n x transpose x. We can verify that this is, if x, I, t are the rows, then this is another compact way of writing it. So this is saying that sigma hat minus sigma in operator norm, if I divide by sigma squared, so what is sigma squared? Sigma is an upper bound on the sub-Gaussian norm of all entries. So this is based on the HDS. So the HDS book uses the sub-Gaussian standard rather than norm, but they're sort of equivalent. So this is saying that so I believe, what do I believe here? I believe what I'm trying to say is, so instead of the psi2 norm, I can just, let's say, define the sub-Gaussian standard of the vector to be just the sub-Gaussian standard of this, the maximum, right? So, or it just, yeah, so what we're saying is something like this, basically, if you want. Xi inner product with u, the sub-Gaussian norm, let's say, squared is bounded by sigma squared for all I from 1 to n and u in S d minus 1. Okay, that's sort of the assumption. Each row is a sub-Gaussian vector with norm control. That's equivalent to saying that the sub-Gaussian norm is up to constant sigma squared. Okay, so that's the sigma squared that appears here. And then I have this bound. There's some sort of a so you can see this is, if you recall, this is the type of sub-exponential bound that you get. So because we're multiplying things that are sub-Gaussian, we expect things to turn out to be sub-exponential. So this is heavier tail than, or has heavier tail than just the previous case where you just had independent sub-Gaussian entries. So you'd expect a more sophisticated tail appear here. But if you ignore this part, so the delta, let's say, if I ignore it, sigma squared for the Gaussian case, at least, let's say, you can say that's bounded by the operator norm of sigma. So if you just focus on this part of the bound, if I multiply this by this part, what I would get is a bound like this. Okay, so this is saying that the operator norm of the deviation is at most root d over n and a plus d over n. Okay, so if, for example, I want to have consistency, you can see that I need n to be, let's say, much bigger than d. So if n is much bigger than d, then which one of the terms would be larger if n is bigger than d? The square root would be larger because this is less than 1. So in this case, this is further bounded by root d over n operator norm. And so if I want this to be less than, let's say, epsilon, what this is saying is that n has to be bigger than or equal to up to constant epsilon to the negative 2 times d. Okay. So this is fairly interesting, although it's like not high dimensional because the sample size or complexity grows with d, but the matrix has d squared, like of the order of d squared entries. So this is saying you don't need d squared entries, like the sample size need not be like d squared. D is enough, okay, to estimate an operator norm, which is quite nice. And yeah, just think a little bit about this. We're not trying to like estimate every entry. So there is some sort of aggregation that happens. Okay, so you need less than basically the number of parameters, in a sense. Yeah.
Two questions. The first one is why all how does it convert rather than
That's what I sort of try to mention. The interesting thing about it is that it's very good to control. It's like the supremum, like maximum eigenvalue deviation. So it controls all the eigenvalues. Like the deviations of the, so if you recall, say the end result here. We have the, yeah, so this is for the singular values, for example, but the same holds for the eigenvalues. There's this Wales theorem that says that the eigenvalues or the singular values, the deviation, say this is a perturbed version of x, right? It's controlled by the operator norm. It's further controlled by the Frobenius norm, but this is a worse, like, bigger thing. So Frobenius norm is larger, and it's often easier to control because you just write down. Can you say that again? Yeah, so if you order the eigenvalues, the corresponding deviations are all controlled by the operator, right? And it's also basically the maximum. It's like the smallest of the unitary norms. So the but the main reason is it's useful for controlling this, and also the eigenvector. So there's this theorem called the Davis-Kahan. So let's go back. So can control eigenvalues via the Wales theorem, and like eigenvectors via something like Davis-Kahan, which we usually don't get to talk about it, but if we talk about PCA, I'm going to talk about this. Otherwise, you guys can talk about it. It's in the chapter, like at least a version is in the chapter about PCA. Okay, so it's very useful to control the operator norm. Then it just translates into immediate bounds on the eigenvectors. And so that was the first question. The
second question is
yeah, so this is not a useful bound for the high dimensional case. But then the thing is, sample covariance itself is not going to be a good estimator in that case. And without adding any more assumptions, there's not much that you can do. So later we're going to like improve this, but you need some sort of sparsity assumption, some sort of, yeah. This is just more general, like what you can do without any further assumptions. Okay, so let's try any other questions. Let's try to set up, I'm going to maybe sketch the proof a little bit. Later, next time we'll come and come back and complete the proof. So the idea is simple. Again, we're going to use the epsilon net idea. So because we're dealing with the symmetric matrices, so I'm going to do so sigma minus. So this is a symmetric matrix. You can show that this is, it's just enough to take the diagonal. So instead of doing like, sigma hat minus sigma x, x. So instead of having like x and y both vary in n minus 1, I can just take them to be the same. For symmetric matrices, this is a simple result that you can show, but you have to put absolute values here. This, for example, follows from the spectral theorem for the eigenvalue decomposition. And the next step is to do discretization. Okay, so by discretization, this is going to be bounded by twice supremum over a net. And then I have the same thing. Let's do U. Right. Sigma hat minus sigma U, and then U. So U is in the net. The net is like 1. Actually, you don't need 1/4. Why did I do 1/4? 1/2 would be enough. So this would be like, but let's say 1/4. Need 1/4. No. 1/2 is enough, right? This is just. Oh, actually, sorry. Maybe. No, maybe it's just okay. Maybe it's still going to be 1 over minus 2 epsilon. Just verify for yourself that you can go through the discretization argument. Still probably you pay this price because I have 2 U's here that I have to control. Yeah, I need that. It's just that I don't need 2 different nets. I can do the same net, but the price that I'm going to pay because of the fact that I have to control both of these U's is going to be 2 epsilon. So do this calculation for yourself. So then we're going to use epsilon 1/4. So this thing is going to be further upper bounded by 1/2. Sorry, yeah, 1/2. The cardinality is going to be 9 to the D. Okay, this is D actually, sorry. So these are D by D matrices, right? They're combined from like there's a summation over n, but each one is a D by D matrix. So you're going to do a D. And so we have 9 to the D here. And then this guy, the strategy is the same. We now have to find the tail bound for this. And you can rearrange it, and this is going to be just a summation. So if you just plug this in here, 1 over n summation xi squared transpose. So you can easily see that this is going to be basically U transpose sigma U, and it's just U transpose xi transpose U. And so this side just translates to this, and now this is a summation of, these are individually, these are, so remember U is in S D minus 1, so these are by assumption sub-Gaussian, the squared would be sub-exponential, so we're looking at a sum of centered sub-exponential random variables. So we have Bernstein type bounds. So you go through like calculation of sub-exponential norm of each entry, and then use the like Bernstein, and then combine with this, and you get the result. So next time we're going to come back as an exercise. If you're interested, you can try to show this for yourself. Try to control the sub-exponential norm of individual terms and write the Bernstein and try to complete the proof if you're interested. Otherwise, we're going to come back and do the thing. Okay. Okay. Thank you, guys. See you next time.